about the dot convention as it applies to mutual inductance or magnetically coupled circuits. You guys were all leaving. Gabriel asked me a fantastic question. Particularly understand the directions on the magnetic flux that I had drawn. And the reason on that there was some coupled amount of magnetic flux. As we established in the class Jace last class, and you guys learned in your we're supposed to be able to and that's not easily conveyable information on a schematic diagram, right? It's hard to look at or counterclockwise around. So in order to uncomplicate that convention that effectively lets us know where a wise wound information that we need when we're going to be dealing with magnetically coupled circuits. So if you have multiple inductors in a circuit and they don't have a dot, what that means is they're not magnetically coupled to each other, so it doesn't matter. If you do see inductors with dots, it means they are magnetically coupled to each other, and the direction of the winding of the coil is important. Okay. We have some excitation source connected to a coil. Voltage V1 of t, and this is our current I1 of t. This one, assumed to be excited. Our voltage V2 of t, and this is our current I2 of t, and we have N2 turns. So instead of having a system like that, with the following diagram. Okay, so over here on over which the terminals over which I'm going to see and all the way out to here. Here is my inductance. Build begins. Then I'm going to have a right-hand circuit. This is going to be L2. I'll put a dot on top of here as well. over this coil, we are going to see a voltage V2. And then out here to the right is my secondary excitation. And now let's talk about these coils in a system. Should have a self component, meaning a component based on the self inductance. So we are going to have where let's assume that I1 is flowing in this direction. And then we're also going to have a mutual inductance term, M is flowing in this direction. We are going to have a similar set of terms over here. So we'll have L2, DI2, by dt. And the last thing that I need to add here, I'm going to erase this to give myself a little bit of space, is I'm going to draw a set of arrows and put an between these two coils. Okay. Well, double-headed arrow points to the two different coils that have that shared mutual inductance term in. So if we were to change the direction on any of these currents or change the location on the dot of either of these inductors, so I am going to do through the way that I have learned to determine whether the self portion should get a positive sign or the mutual portion should get a positive sign for any coil that we're going to be looking at. Okay. So let me write this down really quick. The signs and mutual terms of the induced voltages depend on the direction of current flow. So criterion number one, the self-induced of V1 of t a positive sign if A the positive polarity terminal of terminal and I1 of t enters at the dotted terminal. So if we look at our schematic diagram here, the positive polarity terminal of V1 is on the same node as the dot. Here. The other condition that will give us a positive sign is if of V1 is at the undotted terminal and I1, enters coil number 1 at the undotted terminal, which would be the exact opposite, right? So if I had defined the positive polarity terminal on bottom and if neither of these two conditions are met, the self-term will get a negative sign. The mutually induced component of V1 of t is assigned a positive sign if the positive polarity terminal of V1 is at the dotted terminal two enters coil number 2 at the dotted terminal. So let's look at this really quickly here. So the positive polarity terminal of V1 is at the dotted terminal of coil 2. So the M term here gets a plus sign. If this I2 were entering the undotted terminal, this would get a minus sign. If this if the positive polarity terminal or on bottom or at the undotted terminal, then we get a negative sign. So both of those conditions need to be met. This is something that's maybe a little weird because we're looking for the first part of our condition based on what coil 1 is doing. And then the second part is based on what's going on in coil 2. But what do you guys think the other for giving the mutual term a positive sign is going to be? Effectively, this. So the positive polarity and enters coil number 2. At the undotted terminal. So if these criteria are not met, the term gets a minus sign. For the induced voltage on coil 1, the exact same rules apply to coil 2, right? So if we want to a positive sign, well, is V2 at the dotted terminal of L2? Yes. And the current I2 is flowing into the dotted terminal, so that's why we have a positive sign here. The positive sign here is because the positive polarity terminal of V2 is at the dotted terminal of L2, and current I1 is flowing into the dotted terminal of coil number 1, which is why we get a positive sign here. So if you want to use these rules for different coils, literally just change the subscript notation. That's it. Correct grammar, like I have a degree or something. Yeah. All right, so let's say that we have the following magnetically coupled circuit. Angle 0 degrees volts. We have a 4 ohm resistance, minus J2 ohm capacitor, inductor. Let's put the dot on bottom. And our mutual inductance seen between these two is J4. we have an 8 ohm resistor, a minus J4 ohm capacitor, our ultimate goal is to figure out what the voltage drop is, which I'm going to call VF. So we have not been our current. I'm going to call on random people for things. Alex, the positive polarity terminal of answer, tell me one or the other. 5, okay. So we're going to assign V1 on top. So I'm going to try to sneak. Daniel, should the positive polarity terminal of the voltage V2 be on top or bottom? Good. Bottom. All right. I like that with authority. Mr. Finch, should my Jay, clockwise, okay. So what I am is, before I start doing any circuit analysis whatsoever, this is driving me nuts. Okay. So a self like LVI by dt, well, in the frequency domain, that's going to be J omega L times I. So that's just going to be the impedance times the current, right? So I'm definitely going to have a J6 ohms term, and the current flowing through should that self term have a positive sign or a negative sign based on where the dot is and the direction of current flow, right? So the positive polarity should I get a plus sign or a minus sign? Minus sign term, right? So the mutual term is going to involve this J4. I2. And once again, we need to figure out whether or not the term is supposed to get a positive sign or a negative sign. So once again, the two is flowing into the terminal of coil 2. Positive sign or negative sign? Positive sign. Supposed to be fairly straightforward. Seems to confuse the hell out of people, but I don't particularly understand why. Whatever. I know I'm going to make a mistake right now. Look at what's going on for our voltage V2. The positive polarity terminal is at the undotted terminal of our coil. Be positive or negative? Positive. So we're going to have positive J12 times I2. So I'm just going to write that as J12 ohms times I2. So the positive polarity terminal is at the undotted terminal, and our current I1 is flowing into the I1. Oh, sorry, I got it. I'm used to doing currents in a clockwise direction. I1 is flowing into the dotted terminal. You're absolutely correct. Thank you, Brooke. So let me repeat that. Told you I was going to make a mistake. Positive polarity terminal for V2. Mutual term here should get a negative sign. Absolutely. Okay. All right. So from here, we are now just going to apply Kirchhoff's voltage law around both of these loops, right? So KVL around loop 1. The first thing I see is the negative polarity terminal. And just add that resistor and capacitor together. So that impedance looks like 4 minus J2 ohms to me. Times then I'm just going to add V1 to look like minus J6 ohms times I1 plus J4 ohms times thing right here is just two. So the first thing that I see is V2. So that's going to look like J4 times I1. Just going to make a quick note here that this is just V2. Then I'm going to have, let's see, 8 plus 6 is 14 minus J4. Times I2 is equal to 0. And I apologize for forgetting to put equal to 0 up there. Now I have a the out will simply be I. And we would then throw this into our computer algebra solver like MathCAD or whatever, because this is a system of equations involving complex numbers. How many, if any of you, need a MathCAD review for how to do this? Several hands. All right. Open program. Hopefully this doesn't open up 5 instances of MathCAD, but perhaps it will. Here it is. All right, so due to my impatience, it's opening multiple instances. Oh, good God, looks like 4 of them. Equations, it means we need to be using a solve block, right? So I'm just going to put a solve block in here. My quantities of interest are going to be my mesh currents I1 and I2. So let's say that, I don't like that. Control Shift P gives me my angle sign, 0 degrees amps. Angle 0 degrees amps. Now, realistically, since we're going to wind up using a computer solver for this anyway, we could have literally just said, well, we have this equation for V1, this equation for V2, and then we have this other equation plus V1, V2 plus this thing, and we could solve it as a system of all right, so my first constraint equation is negative 100 angle 0 degree volts plus, what was that impedance? 4 minus J2 ohms. Times negative I1. Then I have my minus J6 ohms times I1. Yes. You're right. It's been 2 months since I did it. Yes, Andrew. Control Shift P. I put an extra negative sign in there as well, so I'm just making all kinds of mistakes here. And then plus J4 times I2. All right, any other mistakes in this? Minus J2 ohms times negative I1 minus J6 ohms times I1. All right, so let's go to our second equation where we're putting in V2. Okay. Times I2, yes. So shift W so that you get uppercase. Any other MathCAD questions? Actually, hit me with them as they come up. Yeah. So 12J ohms times I2. Wrong thing. J ohms times I1. Times I2. All right. Anything about that equation look incorrect? Just as a heads up, for those of you that have had me in previous classes and seen me do MathCAD, you might think I'm getting absolutely ridiculous with the parentheses and all that kind of stuff. But if I don't put a parentheses and then anytime I'm using parentheses is to prevent MathCAD from thinking that some things are functions of other things, which will absolutely break stuff as well. So I'm probably over making sure it's going to come out correctly, but all of the extra syntax is just to try to have as few errors as possible. And solve stuff, so I'm going to use, first thing I'm going to do is put in a simple matrix here, just a 2x1 matrix where my first variable is going to be I1, my second variable is going to be I2, and I tell it numbers in rectangular format, which I generally speaking hate. So I'm going to go into the math formatting here. To do is define V out. Mistaken, we wanted V out times I2, right? Sorry, what did I do there? 6 ohms times I2. And I get a voltage in rectangular form, which does me nothing. 24.828 angle negative 155.55. Each of them in current direction that you guys did. We did it correct. All right. How did you feel about this? Reasonably okay. All right, let's make it fun. So we have been making the assumption that our second, as it were, was part of some separate. We can have two coils in the same circuit that have some mutual inductance with each other, right? Because for that mutual inductance to occur, they just need to be close enough such that some of the flux generated by coil 1 passes through coil 2, or et cetera. So let's consider the following circuit. So I'm going to have a 60-volt source here. This is going to be a J. Here is a J20 ohm coil, dotted terminal. Close this out with a 20 ohm resistor, like so. These two coils, full inductance of J5 ohms. These two coils have a mutual inductance of J6 ohms. And these two coils things going on here, but we can still use those simple rules that we developed earlier, figure out what our induced voltages are. So I'm going to consider the J10 ohm coil to be coil 1, the 20 ohm coil to be coil 2, and the 30 ohm coil to be coil 3. So Grayson, tell me, what should my So let's call this V1. Justin, what should positive polarity be on left, or excuse me, top or bottom for coil 2? Bottom, okay. You guys are starting to see, or maybe turbo. Okay. What about coil 3 blades? Okay. On the right. All right. We're only going to have 2 mesh currents here. So let's see. Read. Mesh current 1, so around the left-hand mesh, clockwise or counterclockwise? Clockwise, okay. And Mason, mesh current 2, clockwise or counterclockwise? Clockwise. Okay. So this is getting a little busy, so I'm just going to put it down there. Okay. So I'm going to approach this just like I approached the previous problem. I'm going to solve for V1, V2, and V3 first, and then we'll plug that in as appropriate when we get to our KVL equations. Okay. Term is going to be involving this J10 ohm term and this current I1. So let's write those down really quickly. It looks to me like The positive polarity terminal of voltage V1 is at the dotted terminal. And our current I1 is flowing into the dot, which means this term should be positive. Coil 2, right? So our impedance is this J5 ohms of mutual inductance between coil 1 and our problem is that a current of I1 through that second coil. So that to me means that we're going to have either I1 minus I2 or I2 minus I1. Okay. So I'm going to choose strategically, as it were, to express the total current flowing through my second coil as I current flowing into the dotted terminal, which will give me a plus sign here because too many negative signs confuses my peon grid. So I'm minus I1. That's total current flowing into the dotted terminal. And because is that clear? There's a lot going on, so I want to make sure you guys are all catching what I'm throwing here. Yeah, to give myself a positive sign. Yeah. All right, so now to account. So that's going to look like this J6 ohm term, the ohm. So let's look. Positive polarity terminal of voltage V1. The current I2 is flowing into the dotted terminal. So that means this should have a positive sign as well. Still hearing whispers. Nobody's asking questions. I feel like my zipper is up, so I don't know what's going on. James. Looking at the voltage at all. I'm trying to find V1. So my interest is in, is this current third coil going into the dotted terminal or the undotted terminal? Because this current I2 is going into the dotted terminal and the positive polarity terminal for V1 is at the dotted terminal of coil 1, that's why I get a positive sign there. So the polarity of this voltage and the polarity of this voltage mean nothing when I'm solving for V1.
So if it was the polarity was negative, V1, negative on that floor.
On all three of these, found everything with currents. Good questions. All right, any other questions before we move on to V2?
Is there any way that we messed up with the problem?
No. To make the currents flow into the That's how I decide what directions my my mesh. So, yeah.
To get to the test. Or not give it a correction.
For a system like this, portion of the test, all I could really ask you guys to do some of equation 3 in this particular instance, because we're going to wind up with a system that you know, computer. I'm not going to make you do Kramer's rule by hand with complex numbers. It would take you 2 hours to solve one stupid circuit, right? This for them was I gave them find the polarities for all of the volts, and then you what I get expressions for the induced voltages. An analysis problem where I actually want you guys to do the circuit analysis, how I'm doing all of these. Does that make sense? Yeah. Okay. Any other questions before we figure? For the self term. And now we have to choose whether we're going to through this particular coin. So all right, so the positive polarity terminal of the voltage V2 is at the dotted terminal, and the current I2 minus I1 is the current flowing into the dotted terminal. So we should get a positive sign for the self term here. Of J5. The only current flowing through coil 1 is the current I1. So now we need to figure out whether this is going to get a positive sign or a negative sign, right? So once again, positive polarity terminal of voltage V2 is at the dotted coil of coil, or excuse me, at the dot of coil 2. Current I1 is flowing into the dot for coil 1. So this should get a positive sign. Now we need to look at our term for the coupling between coils 2 and coil. The only current flowing through coil terminal is at the dotted terminal of coil 2. The current I2 is flowing into the dotted terminal of coil 3. So this one should be positive as well. Anybody have any questions, comments, or concerns about our induced voltage V2? All right, so might get some negative signs because Blaze is a smart ass. Okay, so we're going to be dealing with the J30, and the only current is I2. Roll here. So the positive polarity terminal is at the undotted terminal. And the current is flowing negative. So if V3 were positive polarity on the left and the current flows into the dot, we would have got positive. Because V3 is positive polarity on the undotted terminal and the current is flowing into the dotted terminal, we're coupling with coil 1, so that's going to be our J6 term. Positive polarity is at the undotted terminal. I1 flows into the dotted terminal. We have our coupled term for between coils 2 and 3. Gonna look like J8. And then our current is either I1 minus I2 or I2 minus I1. Okay. Right, so the current of I1 minus I2 is the current flowing down through this branch, which is flowing into the undotted terminal. Since the positive polarity is at this undotted terminal, we'll get a positive sign. Okay. So KVL around loop 1. Like negative 60. Angle 0 degrees volts plus 5 ohms times I1. And then I'm going to leave this as just plus V1 and then minus V2 is equal to 0. And then we would substitute in our expression for V1 and V2. V2 minus V3 plus 20 ohms times I2 on MathCAD, and I don't think we could knock this one out in 10 minutes if we tried. You guys don't have any more questions? I'll see you on Wednesday if you do have questions.